Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 31 of this course on machine learning for art system science. We are in module 4 where we are looking at how machine learning can be used for various art observation system and their applications. The topic of this lecture is satellite imagery as a proxy for geophysical measurements. In this lecture we are going to discuss what are these proxy indices which can be measured from satellites. Then how vegetation, groundwater and soil monitoring can be done using these proxy variables and machine learning measurements, and various applications of earth monitoring using these. First of all, what are these proxy variables? So we know that images are captured by satellites or other earth observation systems. Basically they are images where at every pixel they contain some amount of intensity, and these pixels, as we have discussed earlier also, each pixel corresponds to a special region on the surface of the earth. Now in modern earth observation systems, these images are of very high resolution, and these pixels stand for some very small region on the surface of the earth, maybe a few meters or even centimeters. So basically the satellites are able to capture centimeter level or even meter level information on the earth surface. Now the intensity of the pixel, this can be considered as a manifestation of different properties which are present in that location. That is, the image is captured by as a result of some kind of reflectivity or something like that, but how much light or how much energy will be reflected by the earth surface at that particular region depends on what is present or what is the nature of the surface there. So based on that, based on the amount of reflectivity which is, or based on the amount of intensity which are obtained from a particular region, in images captured at different wavelengths, it is actually possible to calculate certain indices, and these indices can act as proxy variable. For example, a well-known index is called the NDVI, or Normalized Difference Vegetation Index. So it's like saying, suppose we capture two images, one in NIR, near infrared, and the other in the red channel of the visible range. So at every pixel we will get so that is for the same region we will get a NIR image, and we will also get a red image. Now in the NIR image, so at every pixel, I mean at every location, if we carry out this operation, that is the difference between the NIR and the red channel images divided by their sum, so that is known as the NDVI at that particular location. In a sense, this index captures the amount of greenness of that region, and greenness can be used as a proxy for vegetation. So if we if we have the observations from all over the world, from which we calculate this NDVI index in the according to the formula just mentioned. So this is what the NDVI index looks like. So as you can see that there are some regions which are this kind of light green, for which the NDVI value is very high. I mean the NDVI is, because it is normalized, it must lie always between 0 and 1. Now it can happen that in some locations it is closer to 1, in some locations it is closer to 0, and in some other locations it is in between, let us say around 0.5 or something like that. and it turns out that in some of the most forested regions of the world, so let's say in the Brazil, which has its huge Amazon forest, it's mostly green. So similarly, in much of sub-Saharan Africa, which is also densely forested, you see this strong green color. Similarly, in much of these densely forested regions of Southeast Asia, also we see green. On the other hand, in the, let's say in the Sahara desert, in the deserts of Arabia, and also these places of China, the arid regions of China, as well as even in these places like Greenland, where there is no greenery, like there also we see low values of NDVI. While in other moderate like areas which are like densely populated or like built up, but have there is some amount of trees are present, but not like dense forest. So like for example, in much of India, in various parts of Europe and Australia and so on, also in the United States and Canada, we see like around 0.5 value of this NDVI. So basically this NDVI, this is this index can be used as a proxy for vegetation. There are also various other indices which can be defined in this way. So there is something known as leaf area index, LAI, and various other things. So like I leave it as a homework for you to read various or read about these various indices which might be obtained from the satellites, and each of them have like can be interpreted in some particular ways. Now these interpretation will always have some amount of subjectivity. We cannot say like with certainty that if the NDVI of a particular region is close to 1, we cannot say with certainty that there is vegetation. It could somehow be something else also which is for which NDVI is high. Similarly, just because NDVI is say 0.4 or 0.5, like we need not be we need not interpret it in some way. Like different values of NDVI can be attained in different regions for different reasons. However, as a approximate sentence, we can say that high value of NDVI generally suggests a high level of greenery. So now like this property is utilized like as inputs to various machine learning and deep learning algorithms nowadays, and earlier like other simple threshold based mining data mining techniques to like build the maps of some geophysical variables which might be a function of the amount of vegetation in the region. One application of this approach is in this paper, which deals with classification of land cover and crop types using remote sensing data. So deep learning is a powerful state of the art technique for image processing, including remote sensing images. This later describes a multi-level DL architecture that targets land cover and crop type classification from multi-temporal, multi-source satellite imagery. Multi-temporal means taken at different points of times, and multi-source means they are like taken from different satellites or from the same satellite at different like wavelengths. The pillars of the architecture are unsupervised neural network that is used for optical image segmentation and missing data restoration due to the clouds and shadows, and an ensemble of supervised neural networks. As a basic supervised neural network architecture, we use a traditional fully connected multi-layer perceptron MLP, and the most commonly used approach in remote sensing community, random forest, and compared them with convolutional neural networks. Experiments are carried out for the joint experiment of crop assessment and monitoring test site in Ukraine for classification of crops in a heterogeneous environment using 19 multitemporal scenes acquired by Landsat 8 and Sentinel-1A remote sensing satellites. The architecture with an ensemble of CNNs outperforms the one with MLPs, allowing us to better discriminate certain summer crop types in particular maize and soyabeans, and yielding the target accuracies more than 85% for all major crops. So, like here they have compared convolutional neural network with multi-layer perceptrons. So, if you remember in the previous lecture, when we are talking about image fusion from multiple sources, we mentioned this multi-layer perceptron being used for calibrating the satellite and for calibrating ground-based radar and space-borne radar imagery and so on. So, this result suggests that it is possible that convolutional neural networks may outperform multi-layer perceptrons if they are used. So, like some of you may be interested to replicate that paper replacing the MLP with the CNN and see whether you get some better result or not. So, coming back to this paper, so this is what they actually do. So, this is the map of Ukraine, which I guess some of you may have become familiar with due to the ongoing war, but this work was of course done in the like several years before. So, now what they have done is in this map of Ukraine, they are trying to like segment it based on crop types, that is suggest like these colors indicate which crop is being grown in which region. So, first of all they obtain these kinds of so these are the satellite imagery that have been captured. They have some missing data also in the optical images due to clouds and shadows. So, they use some kind of pre-processing techniques to cover them. Then secondly, there is the classification is carried out, and finally some additional post processing data is used to improve these classification maps. So, like when we use the image segmentation, so again so remember that they have not done image segmentation like in the way we discussed a couple of lecture ago by UNet and SegNets etc., but rather they have because their aim is not to separate or segment the region the entire map according to say say this region has water, this region has built up area and so on. Instead what they have done is they are trying to do the segmentation according to the type nature of crops grown in different places. Now like even in a particular region, it's not that throughout the year the same crop will be grown or any crop will be grown. There might be seasons. So, that is why it is necessary in this case they need to consider multi-temporal images, as they have mentioned here, like they need a sequence of images on which they can carry out this kind of segmentation, because like if you focus on the image taken at any particular point of time, some only certain crops will be present. The other areas, even if they are used for developing some crops but at that point of time that may not be the cultivation season, so such crops may not be feasible. So, that is why it is necessary to consider images from a wide range of time. So, like these are that's what they have indicated here, like for which crop they need images from which period of time, and accordingly they have developed a CNN architecture. So, this is what their architecture looks like. They have actually compared two approaches, one is the 1D CNN and the other is the 2D CNN. But like the basic architecture wise, there is no great innovation here, like this is pretty much the similar CNN architecture, but this is the classification results which they have obtained by over the multi-temporal images. Basically the 2D, that is they need to do this 2D CNN because of the presence of multi-temporal images, because they are dealing with not a single image but a sequence of images. That's why they need an extra layer there in this case. So, this is what the segmentation map looks like, and so these as you can see, after the segmentation these different colors stand for different crops that are grown. And now let us come to another application. So, here the task is like they have the the remote sensing satellite measurements of NDVI, which we mentioned earlier also. Now the aim of this work is to measure groundwater level in different parts of India using this like this NDVI. Now this might seem a little bit counterintuitive, that I mean groundwater is something that is underground while the satellite is several kilometers in the sky. So how is it possible for the satellites to measure groundwater? The answer is like the groundwater influences vegetation on the earth's surface. The vegetation in turn is linked with NDVI, that is we have already discussed how NDVI may be used as a proxy for vegetation, and then the satellite can measure NDVI. So like in this 2-step or 3-step way, like we may say that satellite can be like from the satellites it is possible to get an estimate of the groundwater. Of course this is not uniformly like this will not always work very well, as this study itself has shown, because the relation between groundwater and vegetation, this is not a common, like it's like this is not constant, it varies from one region to another. And similarly the relation between vegetation and NDVI, that is also like it's a somewhat dicey issue. So like normalized difference vegetation index or NDVI is widely used as an efficient indicator for vegetation cover. Here we assess the possibility of using NDVI as an indicator for groundwater storage. We use groundwater level or GWL obtained from in situ groundwater observation wells like which are more than 15,000 in number in India during the period 2005 to 2013. Good correlation of more than 0.6 is observed between NDVI and groundwater level in natural vegetation or vegetation covered areas, that is forest lands, shrubs and grasslands, but not in other places like which we will discuss in a bit more detail. We apply artificial neural network and support vector machine approaches to investigate the relationship between GWL and NDVI using both the parameters as input. Artificial neural network and support vector machine simulated GWL matches very well with the observed GWL, particularly in naturally vegetated areas. Thus, we interpret that NDVI may be used as a suitable indicator of groundwater storage conditions in certain areas where the water table is shallow and the vegetation is natural, and where in situ ground observations are not available. So this roughly belongs to that category of work where we have in situ measurements of like a certain variable, and we are we wish to build a continuous map of that particular variable, so that I can get the map get an estimate of the variable at any point I desire. But the only thing is that instead of going for something like say Gaussian process regression or that kind of things which we had discussed in some of our earlier papers, like here they are trying to do it on the basis of remote sensing and satellite imagery. So this is like on the map of India, these are the like this is basically showing first of all the vegetation cover, the irrigation zones and the measurement locations. So these red dots, as you can see, these are some of the locations where in situ measurements are available. In fact, these are only some of them. There are actually, as they have indicated here, there are some more than 15,000 places, mostly wells, where the groundwater can be measured. Now these black dots, what they indicate, these are the places where like the irrigation for farming is done mostly by drawing water from the ground by say something like tube wells or something like that. In other regions of India, when like irrigation is done for agriculture, it's either rain fed or maybe from other sources like say rivers and so on. But in these places, like there is this system of drawing water from the ground and then like pouring that water over the crops and so on. Now we will see how that becomes significant in this study. So this this is like a measure of the water table in different parts of the country. This is obtained by like based on a few in situ measurements and followed by some kind of spatial interpolation. This approximate map is obtained. Here we see the correlation coefficient between rainfall and NDVI, and we, as you can see, that in many places there is only a weak correlation. It's either like quite low, that is say 0.1, 0.2, something like that, or moderate, like in the range of 0.5, but never above that. On the other hand, here this map shows the correlation coefficient between groundwater and NDVI, and here we see the, like, in at least in some places the correlation is actually very strong. So that is, we see quite like these red covers. And now here there are some further studies which this paper has done, like in different seasons as well as in different types of land cover zones. They have carried out the correlation or they have computed the correlation between the groundwater level along the x-axis and the value of the NDVI. So they have done it in agricultural regions, that is where there is a lot of cropping, then in forest regions as well as shrublands. So as the correlation coefficient suggests, in forest regions like which are present in much of central India, like we see like a near like a quite good coefficient of 0.63, which in the earth sciences can be considered as reasonably high. Like there is almost perfect, there is reasonably high correlation between groundwater level and NDVI, which means the greener or more the groundwater, greener that area is. This is true for forested regions. If you consider shrubland, the relation is a bit weaker, but nevertheless some relation is there. That is, more the or higher the water level, more green will the shrubland look. While in case of agricultural region, this is not at all the case. There is very poor correlation between the two. That is because like as I mentioned earlier also, the agriculture, much of agriculture depends on this irrigation. So irrigation can be either rain fed, ground fed, or river fed. So in those places, like especially in large parts of North India, there like where irrigation is drawn, like water is drawn from the ground, the NDVI value might be quite high because it's an irrigated area. So like from the top, like it might appear green, but due to like so much usage of groundwater over these years, the groundwater level has significantly depleted in many of these places. Now this is something which is missed by the NDVI analysis. So like in these agricultural regions, particularly in much of North India, the NDVI can be deceptive as a proxy if we use it as a proxy for groundwater. That is what this paper finds out. So what they try to do, so on the basis of this correlation study, what they try to do is to build some kind of a machine learning model, because we see a reasonably linear relation. So instead of going for any complex or non-linear model like say CNNs and so on, like here they use a simple support vector machine and a simple artificial neural network, where the input is like the groundwater value at that location at time t as well as its NDVI at time t. Now using that, they are trying to predict the groundwater value at time t plus 1. So like the groundwater, as we know, like it has a certain amount of seasonality. It also has a certain amount of this like we can say it has a certain amount of memory, if you want to call it that way. That is, the groundwater is not going to change in a matter of 1 or 2 days. Like if it is already high, it will remain high. If it is already low, it will remain low. It might increase or decrease a little bit, but there won't be any significant change. So that is why it is important to consider the groundwater level at the previous time point also to make a prediction about the future. But the NDVI acts as like you can say acts as a dynamic component for this prediction task. So in this work they have done location based analysis. That is, it's like for every location they have like used this model separately, but like instead of that, if they try to use the like neighboring locations also in making this kind of a prediction, like it may increase or this performance may improve due to the considering the like neighborhood effects. So Now here we move on to another application of these satellite based indices. So here the task is remote sensing for soil organic carbon estimation. Understanding soil organic carbon or SOC is critical to, among other things, atmospheric and terrestrial carbon balance and climate change mitigation. This has necessitated the development of novel analytical approaches to determine the soil organic content. The use of neural networks for analysis of landscape, biophysical and biochemical properties based on remotely sensed data has become popular in the last decade. This has been facilitated by the proliferation of big data from Earth observation systems as well as advances in machine learning. Specifically, the use of traditional neural networks and transition to deep learning frameworks offers considerable improvement in the performance and accuracy of SOC retrieval from remotely sensed data. This paper seeks to provide a brief review on the use of TNN. By TNN we mean traditional neural networks and deep learning based remote sensing strategies in SOC estimation with focus on progression, application, potential and limitations and so on. So like we will not go into the details of this paper, but basically this is like about measurement of soil organic soil organic carbon, and we skip to one more paper. Here the aim is the prediction of PM 2.5, so that we know is like is a measure of the air quality, or like it's a air pollutant, atmospheric. So predicting PM 2.5 atmospheric air pollution using deep learning with meteorological data and ground based observations and remote sensing satellite big data. Air pollution is one of the world's leading factors for early deaths. Every 5 seconds someone around the world dies from the adverse health effects of air pollution. In order to mitigate the effects of air pollution, we must first understand it, find its patterns and correlations and predict it in advance. Air pollution prediction requires highly complex predictive models to solve this spatiotemporal problem. We use advanced deep learning models using graph convolutional network or which is GCN and convolutional long short term memory (conv-LSTM) to learn patterns of particulate matter or PM 2.5 over spatial and temporal correlations. We model meteorological features with a time series of multidimensional weighted directed graphs and interpolate dense meteorological graphs using the GCN architecture. So this is like a somewhat new approach which this paper has adopted, in the sense that the time series of these different variables which they are studying, they have represented it as a graph, and I will show you in the following slides how exactly that representation has happened. But their aim is so they have the graphs at different observation station. Now their aim is to estimate that graph at other locations also, for which they have used this graph convolutional network, which is you can say it's a CNN only, but it in this case the different the input is instead of a vector or matrix, it is something like a graph, and we can say the nodes of the of that graph as well as their edge structure, this is somehow expressed as some kind of an embedding in the neural network. We also use remote sensing satellite imagery of various atmospheric pollutant matters. We utilize government maintained ground based PM 2.5 sensor data along with remote sensing satellite imagery using a conv-LSTM to predict PM 2.5 over the greater Los Angeles County area roughly 10 days in the future, using 10 days of data from the past in 46-hour increments. So basically the source of their data comes from the MODIS satellite, which is at 40 we can say it's available for a particular region over the Los Angeles at 46 hours intervals. So they also apart from this satellite imagery, like an example of which you are seeing here, it's also like they also have various covariates which are meteorological variables measured at 48 stations. So you can say that these are the in situ measurements. So these covariates are the relative humidity, the AQI, air quality index, temperature, air pressure, dew point, heat index, etc. Now from all these things they plan, as they mentioned, they plan to build the map of PM 2.5 in the like in for future, for the next 10 days in future. So now what they do, as indicated earlier, what they want to do is they want to build a graph. Each node in the graph represents the these met variables at each of these locations, and so whenever there are two nodes in a graph, they have to be connected by an edge, and the weights of these edges like depend on the physical distance from their locations, on the wind speed, wind direction, and various other things which they have mentioned. So like as I said, now at a different locations the input is this kind of a graph, and so this is the graph convolutional neural network, the GCNN. So like all the as this figure suggests, so like every hidden node in this CNN like is actually some kind of a representation, or like an or as they say, an embedding of the graph on which the different operations are carried out. So that creates some kind of an like an unsupervised graph representation, that is these graphs that have been provided as input, like it is somehow like we get some kind of a like a representation, and now when the input comes in like from the remote sensing imagery and so on, I mean primarily the remote sensing imagery. So this graph is obtained on the basis of these meteorological variables which already mentioned. Now this this graph is somehow like is merged with the remote sensing imagery as they come in at 46 hours interval, and this merging is achieved with the help of a convolutional LSTM. So how exactly a convolutional LSTM works, we have discussed a bit in one of our earlier lectures, and we will again discuss it in more detail in the next lecture. But finally we get the output, which is the like at any particular location which has been specified here as the input, like it's going to be the output is going to be the PM 2.5 measurements for the next 10 days. So like note that here they are using conv LSTM because it's something like a LSTM, because it's a sequence of maps for the last few days or so, and then like which is obtained by merging the graphs and also from the remote sensing imagery. So we get a sequence of this, so that is why LSTM, and also conv because these are all like spatial maps. It's not a particular location, but it's a map from over the entire region. So that brings us to the end of this lecture. So these are the references of the papers which we discussed in this lecture. So basically the point to be taken away is that different variables such as air quality, soil organic carbon component, groundwater, etc. While these cannot be measured directly from satellites, but there are different proxies, proxy variables, like in some cases the indices like NDVI, in some cases maybe something else or other indices like they like which may have some loose relation between with the quantity of our interest. So that kind of relation, like it's possible, like it may be possible under certain circumstances to parameterize using some kind of a machine learning model, and hence use the remote sensing imagery to obtain estimates of that variable. So that brings us to the end of this lecture. Thank you, and in the next lecture we will see one more application of this remote sensing imagery using machine learning. So till then, bye.